Hi, my name is Shreya Ramesh and I will be presenting my final year project on localization of autonomous racing vehicle through the fusion of GPS and inertial sensors. My project has been carried out together with Monash Motorsport. 2017 was the first year that a driverless competition was introduced at Formula Student Germany, and in 2018, Monash Motorsport began to work on developing Monash's very first autonomous racing vehicle. As an autonomous race car, it should be able to navigate itself in an unknown cone-marked track. Sensors such as cameras and lidars help see the outside world to detect cones and generate a map for the car to navigate itself in. Along with cameras and lidars, sensors such as IMUs and GPS provide information such as where the car is and how it is traveling relative to the environment. After extensive research, the hardware chosen is the Pixie Evaluation Kit. This kit provides GPS measurements via real-time kinematics corrections that requires a setup of a base station. This kit also has an IMU and a magnetometer on board. However, we only obtain raw measurements from these two sensors. Calibrating the IMU, that is integrating the acceleration, shows that the IMU assumes that it keeps on speeding up over time. This could be due to the errors accumulated in integrating the longitudinal acceleration. To accommodate for this drift and misconception, we utilize a Kalman filter to fuse IMU with GPS to obtain more robust information about the state of the car. Kalman filter is a recursive algorithm that estimates the state of a linear system based on sensor measurements and the changing models of the system. The Kalman filter algorithm consists of two steps. The first is the predict step, where the state and its covariance is predicted based on the motion model of the system. And then, in the update step, the filter estimates the state based on the weighted average of the predicted state and the sensor measurements it receives. In the real world, however, most systems are non-linear in nature, something that the Kalman filter does not account for. We use an EKF, that is an extended Kalman filter, to linearize the non-linear model. These non-linearities may arise in either the motion model or the measurement model, or in both. In our particular case, the state of the system is the position, velocity, acceleration, and orientation of the vehicle. In the predict step, the transition or the motion model that maps the previous state estimate to the current state accounts for the transition between the coordinate frames. This is where the nonlinearity arises that has to be linearized by taking the partial derivative of this function respective to the state variable to implement the Kalman filter process. GPS and IMU provide measurements at different rates. To build the model for the update step, as a start, I first synchronized the data collected to account for the asynchronous measurement arrivals. This was done using MATLAB's built-in synchronize function. This step interpolated the missing GPS data to match the timings of the IMU. This allowed me to build the update step before having to worry about asynchronicity. Hence, my measurement matrix consists of the X and Y position from the GPS, the longitudinal and lateral accelerations from the accelerometer, and the yaw rate from the gyroscope. The X and Y GPS positions are only affected by the X and Y state variables. Similarly, the yaw rate is only affected by the change in rotation about the Z-axis. However, the longitudinal and the lateral accelerations are affected by the lateral and longitudinal velocities respectively, as well as the yaw rate. Hence, this gives rise to the following observation matrix. By synchronizing the data and fusing them together in an extended Kalman filter, it is observed that the EKF track map is close to or similar to what the GPS observes. However, based on the fact that there is no ground truth, what we conclude from this is that the extended Kalman filter is accurate enough to mitigate through the weakness of the two individual sensors. Once the asynchronous nature of the two sensors is accounted for, the tuning for the extended Kalman filter will depend greatly on the process noise. To tune the process noise, we look at the situation that the car is in while it moves around on the track. It is expected that the car will not be experiencing a constant longitudinal or lateral acceleration. This gives rise to the concept of jerk, which is the rate of change in acceleration. Taking jerk into consideration and recognizing that this would have almost no effect on the yaw and the yaw rate, the following process noise matrix is observed. This accounts for the difference in time step that the two sensors provide. Going forward, the next step is to implement the asynchronous behavior of the two sensors into the extended Kalman filter. This can be done by splitting the observation model into GPS and IMU model matrices and implementing them depending on which sensor measurement arises. From there, we move on to converting MATLAB code into C++, which can then be combined with the cameras and the LiDAR to help estimate the position of the car, along with providing a map for the path planning section to do their work. Thank you. Thank you for taking time to listen to my presentation.